Okay, so let's get started for today. So last week we discussed steady states, how to find steady states using phase planes and null lines and different types of direction fields. We'll in this week we'll just move them forward. We'll study about bifurcation, how changing of parameters can change your steady states. We'll look into some of the examples of how uh, bifurcation is used in biological systems. Bifurcation theory is used in biological systems, and how we can model these systems and predict steady states. We'll use some examples from ligand binding, and in the end we'll talk about self-head determination and Waddington's landscape. Okay, so let's get started. So first, talking about bifurcation. So we'll first talk about bifurcation and then move into the applications and examples. Okay, so bifurcation in ordinary differential equations refer to qualitative changes in the behavior of the solution as parameters of the equation is varied. These changes can include the appearance or disappearance of equilibrium points, changes in their stability, or emergence of periodic solutions. Now, one thing to keep in mind, if your differential equation has the parameter inside it, so once you are varying the parameter, the steady state will anyway change depending, doesn't matter if bifurcation is happening or not, the steady state will change depending on your parameter. But is the parameter leading to increase, it's the variation of the parameter leading to increasing or decrease in number of steady states, or how these steady states are behaving. If these kind of things happen when the parameters are varied, then we call that there is some bifurcation in the ODE. Then changing the parameters can lead to change in steady states and also in the number of steady states and their stability as well. So we'll look into examples, and then it will be a little bit more clear about how these things work. But mostly these are the four types of bifurcations that are studied. One is saddle node bifurcation, where there is an equilibrium point and a non-equilibrium point. They collide and disappear as the parameter is varied. We'll look into the graphs how each of these bifurcation look. The next one is transcritical bifurcation, where two equilibrium points pass through each other and exchange stability. So basically one will be stable, other will be non-stable, but they'll pass through each other, the equilibrium points. Other types include pitchfork and hop bifurcation. So maximum papers that you see about multi-stability, bistability in biological systems, you'll see maximum systems will exhibit this hop-F or pitchfork bifurcation, but those are a little bit more complicated than the saddle node and the transcritical. So we'll mostly focus on saddle node, but in real life examples, if you read papers related to systems biology or modeling of different cell processes or different kind of processes going on inside this biological system, you'll see these kind of terms there. They are defining what kind of bifurcation is occurring in the system. So this has implications. This helps you study the system and kind of predict where the cell will go, because as you know, we are in this course we are studying the dynamics of the whole system using ODE. So biological system inherently are very dynamic in nature. So over time, certain processes will go on, certain proteins will be formed, certain transcription factors will regulate gene expression, and so on. Like various kinds of processes will be going on inside the cell. So these are dynamic processes. And why do you need bifurcation to study dynamic processes? Just to predict from, like, if we know the system is in this state at this point of time, at a later point of time, how can the system behave? How will the system behave? Will it move towards one stable point? Will it move towards another stable point? Actually, what are the possibilities of that cell of that process to evolve? So that is the whole crux of studying bifurcations of ODEs in biological systems. Key to predict what kind of states or what kind of stability points will the system converge or diverge from. So yeah. So as I was saying, these are the different types of bifurcation plots. So this is the saddle node. You have so basically the stable equilibrium is given by the blue one and the unstable is given by the red one. The saddle node bifurcation, you will see there is one point around which there is the there is one side is the stable, unstable equilibrium, and the other side is the stable equilibrium. Okay, sorry. So so this is the kind of bifurcation that will be mostly studied and used in examples from our side for this course. We'll mostly focus on bifurcations that are ultimately leading to saddle node bifurcations, but these are the other types of bifurcations as well. So one thing to keep in mind, these are called bifurcation plots. So when you are making bifurcation plots, one thing need to be clear, that you are plotting x versus alpha. If you remember, in steady state, while plotting steady states and different type of phase planes, we were plotting dxdt versus t, or the rate of change of your dependent variable versus your independent variable. But in this case, since what we want to know is how our stable states or how our system is changing over the change of parameters, so the bifurcation plots will be your dependent variable versus the parameter, and these kind of plots will be generated where you can like see around which point there is stability or there is instability, and how varying your parameter, in this case this is given by alpha, how varying your parameters can change your number of steady states and even types of steady states as well. So let's first see an example. Okay, so yeah. So where's my pen? Okay, so let's take this example first. So say you are given a differential equations. Yeah. Say you are given a differential equation like this, dx dt equal to x square minus 4x plus lambda. So here lambda is given as your parameter. So, and you are asked to draw the bifurcation plot for this OD. Okay, so let's look at this differential equation. So it is given as dx dt equal to x square minus 4x plus lambda. Now let's look at different values of lambda and how, like, our idea is to check how x is changing with the variation of lambda, and how it is attaining steady state or it is not attaining steady state. So let's first take a random lambda point. Let's start at 0. At lambda equal to 0, dx dt, just you substitute the value of lambda here, it will be x square minus 4x, it's plus 0, so I'm not writing it. Now at steady state, as you remember, we define steady state like this, dx dt equal to 0. Since this is one, there is one dependent variable in this equation, so equating that variable to 0 is enough for this one. But when you have multiple equations, you need to, if you remember from last class, we will have to draw null lines for the dependent variable. So there will be one null line where dx dt equal to 0, that will be one curve or a line, and there will be another curve or a line where dy dt equal to 0, and in the xy plane where these two lines will meet will be the steady state, and individually these lines are called null lines, just to recap from last class. Now at steady state, since this is one dependent variable containing ODE, so dx dt equal to 0 at steady state. Now if dx dt equal to 0, then x square minus 4x equal to 0. You take x common, x minus 4 equal to 0. So there are two values of x here. x equal to 0 and x equal to 4. Now there are two steady states here, right? X equal to 0, x equal to 4. Now you need to find if they are stable or unstable. I'll just do this for one example. For the next times, since I've already solved this sum, I'll tell you which is a stable or which is unstable. Now if you remember from last time, let me see if I can bring it up last time. Yeah, if you remember, this problems we were working on the last time in the last class. So this is how we calculated stable or unstable steady state. So for different values of x, we calculated dx dt. So basically this is the steady state, where dx dt equal to 0, and we checked for values of x in and around that value and see if basically the process is converging at the steady state or diverging from the steady state. In this case, this was diverging. So basically what it meant is it's an unstable steady state. If it is converging towards the steady state, it will be a stable steady state. Okay. Now let's try to check that. So dx dt equal to 0 at x equal to 0. So let's first take the x equal to 0. So this is your x, this is your dx dt, this is your sine, and this is your arrow. Okay. Now dx dt at, sorry, there's another. Yeah. So dx dt equal to 0 at x equal to 0. There's no sign. Okay. Now let's take a slightly higher value than 0. Let's take x equal to 1. At x equal to 1, if you substitute x equal to 1, it becomes minus 3. So x square minus 4x. Substitute x equal to 1. You substitute x equal to 1, this becomes 1 minus 4 is minus 3. So the value of dx dt is minus 3. Sign is negative, arrow is it's inside. Now let's take a slightly lower value than 0. Let's take minus 1. So if you put x equal to minus 1 here, I'll just use the eraser here. If you put x equal to minus 1 here, so this becomes 1 minus of minus 4 becomes 5. So x squared minus 4x is 5. So this is a positive value, this is a positive sign here, and it is converging here. As you can see, so x equal to 0, this is a stable steady state. Now let's do for x equal to 4. Same method. So at x equal to 4, dx dt equal to 0. Okay, let's take a slightly higher value of 4. So let's take 5. At x equal to 5, let's do the calculation here only. So at x equal to 5, this becomes 25 minus 20 equal to 5. So at x equal to 5, dx dt equal to 5. This is positive, arrow upwards. And let's take a slightly lower value than 4. Let's take it 3. Now let's check the value of dx dt at x equal to 3. X equal to 3, this becomes 9 minus 12 equal to minus 3. So minus 3 negative, so down like this. So this 4 is an unstable steady state because your system is diverging from that steady state. So this is unstable. You can do this using the direction fields as well. You can check how the direction fields are moving about this point to check if it is stable or unstable. This is a simpler way to calculate if your steady state is stable or unstable. Okay, so there are two steady states here, so just let me write it down below again. So we took lambda equal to 0. There were two steady states, x equal to 0 and x equal to 4. So this is unstable. Since this is stable, 0 is stable, all the basically the process will converge to that steady state. So this is what is known as a sink, and this is what is known as the unstable one is known as the source, because it is like this. So for example, if I am drawing the phase plane x versus t like this, so at x equal to 0 and x equal to 4 like this. Sorry, this looks a little bit weird. Let's see, this is x, this is 4 and this is 0. So at 0, all the arrows are converging here from both the sides, from top and from bottom, as we see here, from the positive and a negative end. So this is how the phase direction field will look like around 0. So this is what is known as a sink. So basically everything is going there and converging, and along 4 what will happen is it will diverge. It is moving away from 4 like this. So this is what is known as a source. So these are just extra terms to like help you get acquainted with, but do not worry about this terminology. You need to know how the steady state is behaving in terms of the actual behavior. Is it moving away, or is it converging, or is it diverging? So that is a more important thing. Okay, so for lambda equal to 0, we have two steady states, at x equal to 0, at x equal to 4. Now let's take some other values of lambda. Say lambda equal to 4. Now lambda equal to 4, this was our equation, dx dt equal to x square minus 4x plus lambda. Now you substitute lambda equal to 4, which becomes x square minus 4x plus 4. Sorry. Now say at steady state this is equal to 0, which if you factorize this is basically x minus 2 whole square equal to 0. It implies x equal to 2. So if you check this steady state at x equal to 2, what will happen is x equal to 2 will be somewhere here. So if you draw a line here, so from one side it will be on the top, from the top side it will be converging, and from the bottom side it will be diverging. So 2 here is basically what is known as a semi-stable state. So from it is basically one side converging, the other side is diverging. This is what is known as a semi-stable state. Okay, so at lambda equal to 0, we saw there are two steady states. At lambda equal to 4, there is one steady state. Now let's take a slightly higher value of lambda again. Let's take lambda equal to 8. Now dx dt becomes x square minus 4x plus 8. Now if you try to factorize this equation, if you just try to kind of use the quadratic formula, so x equals to minus b, so this is 4 plus minus root over b square minus 4 this is c and this is a by 2. This 2 because the value of a is 1. Okay, now if you notice, this term under the root is a negative term. So under the root negative, this is a complex root. So basically there are no real roots, real solutions of x when lambda equal to 8. So x has no real solutions. In fact, if you just take the whole equation x square minus 4x plus lambda equal to 0, and you try to factorize this for all values of lambda. So in this one, x will become minus 4 plus 4 root over b square minus 4 lambda by 2, right? Now since for x to have real roots, this thing under the expression under the root over should be a positive one. So 16 minus 4 lambda equal to 0, or not equal to, should be greater than equal to 0. Sorry, let me write it properly. Should be greater than equal to 0. Then 4 lambda becomes less than equal to 16 and lambda becomes less than equal to 4. So what is this telling you? This is telling you that your lambda needs to be less than equal to 4 for this particular equation, or for this particular expression, the algebraic equation, to have real roots, for x to have real values. So as we checked here, at lambda equal to 8 there is no real value. So from here it is telling you that any value after lambda equal to 4, be it lambda equal to 5, 6, 7, 8, for all those values, the basically the x will not have real solutions, it will have complex solutions. So at this point, beyond this point, there is no steady state for x. So now let's try to do the bifurcation plot. Just a second. Okay, I'm a little bit surprised nobody has joined yet, apart from you, so I'm just checking. Okay, let's go on. Do you know any reason people have not joined or anything?
I don't know.
Oh, okay.
Maybe they tried 2 assignments, and last week we got solution for that.
Okay,
Maybe,
acha.
I don't know.
Okay, no problem. No problem. Okay. Acha. So yeah, now like we checked lambda for values of 0, lambda equal to 0, lambda equal to 4, also greater than 4. So let's try to do the bifurcation. Let's see how the bifurcation plot will look like. So for bifurcation plot, remember we plot x versus lambda. Okay, x versus lambda. Now let's do 1, 2, 3, 4, 5. This is 1. Now so basically x is given in your y-axis. So for x equal to 4, for lambda equal to 0, you have two values of x, 0 and 4. So lambda equal to 0 is given by the x-axis. So 0 and 4 are the two values of x for lambda equal to 0. Now for lambda equal to 4, we calculated the value of x is 2. So for lambda equal to 4, it will be somewhere here. So if this is the 4th. Okay. So for lambda equal to this, I'm just writing here lambda equal to 0. So for lambda equal to 0, let's highlight with another color. These are the 2 points for lambda equal to 0. And this is the point with lambda equal to 2. Now this has given you the phase plot. This has given you the bifurcation plot. How? Just like this. Sorry. this is how your bifurcation plot looks like. If you start increasing from lambda equal to 0 to till lambda equal to 4, at 4 you will have only one steady state around this steady state, and basically if you check for lambda equal to 1, there are two steady states of x, here and here. For lambda equal to 2, same here and here. Lambda equal to 3 as well, these 3 points. But at lambda equal to 4, this basically the curve takes a U-turn like that. So beyond lambda equal to 4 you cannot go. So this is how your bifurcation plot looks like. So let me draw the lines here as well. Yeah. So this is how your bifurcation plot will look like when you vary lambda with x. So just to go over what we did here again. So this was our equation. We found different steady states for different values of lambda, and we checked if the steady states are stable or unstable, and then we plotted this. So basically these two steady state, these are two steady states for lambda equal to 0, and for further values of lambda we plotted different steady states for x, and we plotted the graph. So basically this is how you draw bifurcation plots. So this is what is known as a bifurcation plot. So for any equation, you try to find out the different values of lambda for the different values of x, and then you plot a lambda versus x curve. So that is what is giving you basically different values of x for different values of lambda, and how your system is changing with the values of lambda. So basically this is what is known as a bifurcation plot. So if you notice, this is what notice looks like something like this, which is known as a saddle node bifurcation. So as we said, in most examples we'll use these kind of examples only where it is doing saddle node bifurcation, but you can have more complex types of bifurcation like these and these, different type of pitchfork or transcritical bifurcation as well. So there can be other types of plots as well. Now let's see another example. Okay. Now let's take another example, dx dt. Sorry, this is I think too dark. Yeah. Let's take this equation, dx dt equal to mu x minus x cube. Now let's try to find steady states for this equation. So mu x minus x cube, basically a steady state, this will be 0, x cube equal to 0. Takes x common, mu minus x square equal to 0. So there are three solutions from this equation. So x equal to 0, and the other one is x equal to plus minus root over mu. So basically if you take mu minus x square equal to 0, this is what will come to. Okay. So there are three solutions, three possible steady states here. So at x equal to 0, or x equal to plus root over mu, or minus root over mu. Now let's x equal to 0, so it's given, like it's a straightforward thing. Now let's check for different values of mu how it depends, how x depends on different values of mu for the steady state. Now if first condition is if mu is greater than 0, so there will be two roots for it. So x will be root over mu and minus root over mu. Okay, because mu is greater than 0, so this works. Now if mu is equal to 0, then x is equal to 0 from x equal to plus minus root over mu. It's straightforward. Now the third scenario is when mu is less than 0. Here the roots will be complex, which is basically not real. Okay, so there are three possibilities for the value for mu to, sorry, there are two possibilities for mu to happen. Either mu can be greater than 0 or mu can be equal to 0, because if mu is less than 0 you will have complex roots basically which will not a biological system can't have complex roots, some like that, right? So if your x cannot be complex, x is a concentration of something or anything else you are modeling, so x cannot be a complex number. So the last, this one is not possible only. So mu can be either greater than 0 or equal to 0. Okay, so for greater than 0 you have x equal to, so let me just write down here. So how is the relationship between x and mu looking? So x equal to, let's write it like this, x equal to sorry, x equal to root mu when mu is greater than 0, also minus root mu when mu is greater than 0 as well, and the third is equal to 0 when mu equal to 0. Excuse me. Now how will the bifurcation plot look like? If you imagine, so let's make it bigger here. So if you are plotting mu on the x-axis and x on the y-axis like this. Now for mu greater than 0, so for this part of the plot, mu so it's basically plus root mu and minus root mu. So basically x square equal to mu, right? So your curve will look like this and like this. And now if mu equal to 0 at x equal to 0, that means this point is also included. So your curve will basically look like this parabola, right? So I just combine the first two conditions, just squaring x square equal to mu. This is basically a formula of a parabola. Okay, so this is how the parabola will look like. So I hope till now you have gotten to know how you can plot this bifurcation plots. So for complex equation, what you can do is you can like use those plotters and every like other softwares there are for plotting and seeing the phase planes and how the steady states are changing. But sir has insisted me to work these out in like using pen and paper, because in your exams also and also for your understanding as well, if you can practice using pen and paper and try to draw these bifurcation plots by yourself, that will be much more helpful than using some software that will do it for you. For your understanding, I'll strongly suggest that you try to do these kind of basically different types of steady states and everything, how you are finding and plotting this bifurcation plot using pen and paper. Okay. Achha. Now let's move on. So this is how basically another bifurcation plot will look like. This is also a saddle node bifurcation. So around this point, one side is stable, another side is unstable. So this is the bifurcation plot for this equation, dx dt equal to mu minus x square. Okay, so just to give you an example how it looks like. Okay, so now we saw how we can calculate bifurcation.
Hello.
Yeah.
Here they didn't mention mu explicitly, right? So how you can plot that? I mean, how you find the stability?
So for this example you are telling?
Yes.
Okay, so mu has not been given to us ki what is the value of mu, but we are assuming different values of mu and checking how it is varying with x. So for mu greater than 0, this is the relationship between mu and x. For mu equal to 0, this is the relationship between mu and x. And for mu less than equal to 0, there is no relationship between mu and x. So we are checking at different places for different values of mu, how is x varying. So that is how we are getting the bifurcation plot. So they have not told us anything. What is mu? What is exactly the value of mu? What we are doing is we are assuming different values of mu, and we are checking how x is varying accordingly, right? So they have not given us anything. But if they had given us a particular value of mu, then we could have directly found out a particular point in this plane. Ki for mu equal to this, say for mu equal to 0, x is 0. Right, so if mu had been 0 here, so this would have been x cube equal to 0, so which means x equal to 0. We are just assuming different values of mu, just we can get how x is changing with different values of mu, that's all.
Okay.
Yeah, okay. Yeah. Okay. So we saw how to calculate these bifurcation plots and how to do these plots. Now the point is, why do we need to do it? Like, what is the use of bifurcation in biological systems, or how can we quantify bifurcations in biological systems? So here are a couple of examples. So in population dynamics, how bifurcation theory comes in handy. So basically, if you remember, this is basically the Lotka-Volterra equations that we saw last week as well, doing the predator-prey models as well. Those are the name of the equations are known as the Lotka-Volterra equations. So basically, it is a classical model in ecology that has been used for many years to model the relationship between prey and predator and have an appropriate dynamics for this. But these kind of systems, what they do is they exhibit this kind of bifurcation behavior. So changes in the parameter can lead to change in the number of steady states and the types of steady states that was there. So what are the parameters here? If you remember the predator-prey model, there was the carrying capacity, there was the birth rate, there was a death rate. So how changing these different parameters, how changing the carrying capacity can change your steady state, or the number of steady states possible, how changing the birth rate or the death rate can lead to changes in the stability of the system, resulting in oscillations, extinction or coexistence in population. So what we look from these bifurcation plots is basically how our system can evolve with time and what kind of steady states can it achieve. So, and that if that particular thing, what kind of and how many steady states a particular system can achieve, that is dependent on the lambda, or basically the parameter values of your equation. In this case, in the case of predator-prey models, parameters like carrying capacity, birth rate or death rate, then you can see bifurcations in the system. So there will be basically there can be multiple steady states in the system, and then what will lead to is basically what we call as bistability or monthly stability. Like, there are multiple points in the system where it can achieve stability, and how it is achieving stability, how it is evolving with time and evolving with the variation of the parameter, how you can vary your parameter to push your system towards stability or to pull out your system towards stability. So if you want to know that these kind of behaviors, what you need to do is this kind of bifurcation analysis, bifurcation plots. Same with the case of epidemic models as well. So if you remember, we took like basically certain parameters, like, let me go back to the notes. Yeah, so in the pandemic model also we have this R parameter here, right? So how the variation of R can change the steady states of this whole system or the whole model is what we are looking to gain from bifurcation plots as well. In this case, it does not depend much on R, but in other cases, if you have a bigger equation, it will depend on R and how R is changing your number of steady states and the types of steady states achieved. That is what we are looking for from the bifurcation plots and bifurcation theory. Okay. So this will come to a little bit later. Okay, let's try another one actually. No, okay. This actually I explained. If you saw mu x minus x cube, so this is how it is changing. At one in this both this side, it is basically a stable equilibrium for both x equal to root over plus mu and root over minus mu. It's both a stable equilibrium. Here is the point of bifurcation, here at which is the point changing. So for mu equal to 0.5, you will have two steady states here, right? At mu equal to 1, you will have two steady states, but at mu equal to 0, you only have one steady state. So at this point, it is basically bifurcating. So this is what is known as the bifurcation point. And at x equal to 0, it's basically this line is what is the stable for mu equal to 0 and unstable for mu greater than 0. So this is another steady state that is given by x equal to 0. But the whole idea is how your x is changing with variation of mu. If you increase mu, what is happening? If you decrease mu and bring it to 0, what is happening? This is what you want to know from the bifurcation diagram or the bifurcation plot. So if the variation of the parameter changes the qualitative behavior, this qualitative behavior is very important of the steady state, we call it bifurcation. Now one thing to remember, changing the value of mu, just changing the value of mu will automatically, like what to say, increase or decrease your steady state, because your whole equation is dependent on mu. But if changing the mu changes qualitative behavior of the system, then what we say is bifurcation. So by qualitative behavior, we mean changes in number of steady state or changes in the stability of those particular steady states. If these two particular things happen, then we only call it bifurcation. Other than that, if you just change your mu, your steady state will either increase or decrease. That is not bifurcation. Bifurcation is when the number of steady states has increased or decreased and the stability of the steady states have also been changed. So that is when bifurcation occurs. Normal changing of parameters, just increasing or decreasing of parameters will automatically affect your steady state because it is part of your equation. So that is not bifurcation. Just to be clear, there is a clear distinction between bifurcation and just the variation of your parameters. Variation of your parameters does not guarantee you bifurcation. Bifurcation will only happen if the system is set up like that if you vary your parameter, your number of steady states will change. It is then you will call it bifurcation. Just to give you a clear idea, this is what we mean by bifurcation, and this is where we apply how we apply bifurcation, right? Okay. So the next part of today's live session is basically we'll talk about different type of motifs and different type of basically how we model this biological phenomena using ODEs. So network motifs are basically the smallest repetitive parts of a network. So imagine you have a very big network. In the whole network, say a particular protein is being synthesized, and in the whole synthesis process of this protein, there are small sub networks in the whole network, which is basically doing a transcription or a translation or a replication. These are small things that are happening inside the network, but on a repetitive manner. So that is what we call as network motifs. So network motifs are patterns of interconnections in complex networks that are more frequent than in randomized networks. So if you take a random network with basically no prior information altogether, you just randomly pick up nodes in a network and you just connect them. So the network that is formed, if you compare that network to your original network, what you'll find is your original network has some particular shapes or particular group of nodes which are together always or which are connected always, that is not found in the randomized network. So that is how we define network motifs. So these are these patterns of interconnections in complex networks that are more frequent than in randomized networks. So basically these are what defines the network. These are what basically drives the function of the network, how the network is interacting and working and basically giving you outputs. These network motifs actually drive that. Okay. So these are small connected subgraphs that can be used to study networks from different perspectives. Network motifs can be found in many biological applications using gene regulatory networks and biochemical networks. So different types of these network motifs will come to in the later slide, but this is basically what the network motif and how it is how they are modeled. So for example, take these on the left, equations on the left. So basically this is M and this is M phosphate. So basically there is one kinase. Kinase is an enzyme that attaches a phosphorus group to a compound, and the opposite of a kinase is what is known as a phosphatase, which basically pulls out a phosphate group from the compound. So for example, this, if you check this network, your M is being converted to M phosphatase, phosphate, not phosphatase, M phosphate by addition of a phosphatase. M is getting converted to M phosphate by the addition of a phosphate group, and which is aiding this addition of a phosphate group is basically this enzyme, which is the kinase, this kinase. And this is the forward reaction, and this is the reverse reaction where your M phosphate is getting converted to M back again with the help of this enzyme, which is the reverse of kinase, which is phosphatase. Now again, this M phosphate is actually inhibiting the expression of kinase. So basically kinase is converting M to N phosphate. Now the result, the product of this reaction is inhibiting the enzyme of its reaction. So basically it is self-checking itself. It is basically a feedback loop, but it's a negative feedback loop that is being shown here. So basically this is how you, for different types of these models, different types of these, if you see, if you compare these two, there is an added repression here. So this is a slightly different version of this one. So there are different types of these models, and what you do is you model this. Basically you try to model the whole equations and the reactions that is happening here. So this is, you write down the reactions and you, like using Michaelis-Menten law, you model these equations, and what you get is basically bifurcation plot. So basically this is your parameter and this is your basically X or M or whatever you're plotting. So you plot your parameter versus your response, and this is what you get as your bifurcation plot. So from here you know that from till this point there is one stable steady state. If you consider this and this area, sorry, I'll just, I'm not sure if I can, if you consider this area on the left, basically this has only one steady state, stable steady state. If you consider this area between these two lines, so this has, so for one parameter value it will have 2 or 3, this is not actually a steady state, I'll just remove this, just ignore this, but basically you'll have 2 steady states here, and on the right again you'll have another single steady state. So this is how the dynamics of the whole system is modeled. So you have a reaction, you use Michaelis-Menten equations to model the whole reaction, and you check for bifurcation in the system. Is there multi-stability, is there bistability? So this is one type of basically dynamics that is possible. Another type of dynamics that is possible is basically oscillating dynamics. You plot your X versus T and you see it is oscillating. So this is also very possible, which is done by, like, if you have motifs like this is very possible, like this will form an oscillating system. So this, you need to model the whole system in terms of differential equation and using Michaelis-Menten constants, and after that you try to plot your dependent variable versus the parameter, and this is what will give you the dynamics of the system. So you check for multi-stability and you check for if the system is oscillating or how is the system changing with time. So this is the whole idea why we do bifurcation plots, why we try to do phase planes and try to see how the system is converging or diverging. So because at the end what you want to know from your model is basically how my system is behaving, be it how it is achieving steady state or how many steady states are possible for that, and how if I vary my parameters, my steady states and my equations and my reactions can change. So this gives you a power of understanding how your system is evolving with time, and that is the thing that you are trying to model. Okay. Now, there are different types of this network motifs. So there can be, like, inside a motif, there will be interaction between two particular genes or two particular elements of your network. That can be genes, that can be transcription factor, that can be other things in the cell as well. So there can be different types of interactions happening. So one such very easily found interaction is basically positive. Basically positive feedback loops, right? So positive feedback loops is it's quite simple. So this is a very actually, if you see this one, this is a very intuitive example of a positive feedback loop. So what is happening is here, so there are three players here, X, Y and Z. This can be molecules or genes or cells, anything. So X is increasing the expression of Y is increasing the expression of X. So both are positively regulating each other. Same with Y and Z, both are increasing their expression. Same with X and Z, both are increasing their expression. But along with that, even there are these nodes, basically these genes or these proteins, whatever they are self increasing themselves as well. So there's a positive loop. So the more a particular of these X, Y and Z is expressed, the more feedback it will give and express itself more. So basically this is a fully connected, what it's called as a fully connected triad. So there are three players which are positively regulating each other and also positively regulating itself as well. So this is a regulated double positive. So basically you have two elements where basically they are positively regulating each other and positively regulating itself, and there is another player which is basically positively regulating both of them. So what you do is from this is basically write down differential equations and check how X is changing with time, how Y is changing with time, and how Z is changing with time. So this is the kind of dynamics you'll get. Okay. This is the kind of dynamics you'll get. So for example, Z, after a certain time it increases, but it again decreases. Y, after a certain time it increases and stays on. X also, after a certain time it increases and stays on. So this is how the system will behave. This is how you predict how the system will behave, because if you have things like this, if you have networks like these or these, any kind of networks, what you do is you try to model them and check how that particular thing is varying with time. So developmental transcription networks often use positive feedback loops that are made of two transcription factors that regulate each other. So these are types of loops that you will find in itself only. So I'll just show you. I worked on one such loop. So actually I have a paper regarding that. I'll just show you. So so here what we studied was the so I'll just give you a context before I tell you about the paper. Actually it's in the paper itself only. There's the network. Yeah, so I'm not sure if you can see or not. So this was the network. So I'll tell you a little bit more. So A, B, C are three cell types, three different T cell types. So there are T cells, but T cells also have different types of division. So T cells have specific T cell cell types as well. So TH1 is one cell type, TH2 is another such cell type, and TH17 is another such cell type. Okay. So what we saw is basically these cell types, TH1, TH2 and TH17, they had some master regulators. So what happens is T cells have what we call as a T progenitor cell. So T progenitor cells are basically stem cells which give rise to these kind of T cells, Th1, Th2, Th7. They are coming from a same ancestor. They are same stem cell which is getting divided into different types of cells. Now this cell, this network, what it is depicting is, so if the stem cell is converted into Th1 cell, during that conversion it will inhibit the process of Th2 and Th17. So Th1 will inhibit Th2 and Th17, Th2 will inhibit Th17 and Th1, and similarly which Th17 will inhibit Th2 and Th1. Now how do we know this? We know this from RNA-seq data, or from basically gene expression data of these three transcription factors, Tbet, GATA3 and ROR gamma T. So these three transcription factors, these are known as master regulators. So if the T cell is getting formed into Th1, that is because of the expression of this particular transcription factor. If the T cell is getting converted to Th2, then it is because of this transcription factor, and if it is getting converted to Th17, it is because of this transcription factor. But all these transcription factor, they negatively regulate each other. So if one is getting expressed, the other two won't be getting expressed. So what we did was we modeled this using ODEs, and we checked for different dynamics and how this dynamics is varying. If you see, there is a lot of oscillation in the system from these graphs as well, and we wanted to check what kind of feedback mechanisms are going on and everything, and we also validated these using, we also validated this using publicly available RNA-seq data. So these are very these are very commonly used methods that are seen if you check different papers and all. So these are very commonly used methods to model the system. So this is basically, for our case, sorry, the website is a little bit weird. For our case, this is what is a completed. This is basically our network motif. This is our lowest form of, basically the lowest subunit of the network that will repeat itself. So this is our network motif, and we are trying to model this network motif to get an idea about how our system is working, right? So this is the type of things that you will do with this kind of modeling. Okay. Okay, now moving back. Yeah, so we talked about positive feedback loops, same with negative feedback loops as well. Negative feedback loops between two genes or proteins are often made up of interactions that take place on different time scales. For example, X can slowly activate Y, which in turn quickly inhibits X. This can happen. So these time periods are also important. So how will you model this when you're modeling this? How will you take into consideration if the activation or the inhibition is slow or fast? This will be given by your parameters. So you will choose, when you are modeling this repression, Y repressing X, when it is happening, the parameter that you will choose, the rate at which this will happen, will be much lower in this case, much higher in this case, because this is a fast, and when X is activating Y, this will be a much slower reaction. So your parameter will be slow there as well. So just a second. Okay. So when you are modeling all these, there comes the importance of parameters. So you can modify those parameters to fit in these assumptions that X is activating Y in a slow manner. So your parameter used there will be a smaller one. The value of the parameter will be small, and if it is inhibiting or activating in a fast manner, then your parameter will be larger. So in this one, X can slowly activate Y, which in turn quickly inhibits X. which for example slow transcriptional activation and rapid inhibition by degradation. This is something that is quite commonly seen in the biological cell system, and these particular circuits can create oscillations. So what will happen is, at one point of time your X will increase, along with that your Y will increase, because again Y is increasing, X will be decreased, so again your X will be decreased. So you will have an oscillating function where your concentration of X and Y will oscillate over time because of this behavior, one like activating and the another inhibiting. Now depending on this rate of these fast and slow reactions, depending on this will depend how far will it oscillate. Will it oscillate and converge to a particular expression level, or will it oscillate and oscillate till infinity? So these kind of things can be like defined by your parameters, and these kind of models you can do by modifying your parameters. But these are what are known as network motifs, as was the last one, positive feedback loops and negative feedback loops. So these are the smaller subunits of your network which you try to model using differential equations, and you check how your system will evolve with time depending on these equations, right? Okay, so another few types of regulation that happens basically in network motifs that you will see is, one such is basically auto-regulation. So it is so the expression of a particular gene or a transcription factor will regulate itself. So if it is, so for example in the negative autoregulation case, so if X is increasing, it will repress its own expression so that it cannot increase till infinity. But if X is showing this positive kind of feedback loop on itself, autoregulation, what will do is it will increase and increase, because X will increase, then by that loop again X will increase, and it will go on like that. So it will go on and increase like that. So there can be different kind of this autoregulation, and autoregulation is something that is very commonly seen in biological or biochemical networks. As I was showing you for the T cell example as well, there is autoregulation. Those transcription factors that inhibit each other also basically increase their own expression, positively regulate themselves as well. So autoregulation is something that will come across very often in biological systems, and basically this is how you can move forward with them. Sorry. Okay. So autoregulation occurs when a transcription factor represses the transcription of its own gene. This is this case, negative autoregulation. This occurs in about half of the repressors in E. coli, and this can speed up response times of gene circuits and reduce cell-cell variation in protein levels, that due to fluctuations in production rate. Positive autoregulation occurs when a transcription factor enhances its own production, as in this one. Response times are slowed and variation is usually enhanced. The motif, given sufficiently cooperativity, can lead to bimodal distributions, basically bistability, what it is doing, where the concentration of X is low in some cells but high in other cells. So what will happen is, there will be two steady states. In one steady state you will have X will be lower in those steady states, and the other steady states X will be higher. So it will be a bistable system, possible bistability, right? This is possible. Okay. So another type of motif interaction is basically cascades, which have X is influencing Y, Y in turn is influencing Z. So as you can see from the figures given here, cascades of gene expression create sequential activation of genes. Downstream gene is activated when its regulator reaches the relevant threshold. Using negative regulation, the genes can be sequentially activated or depressed. So depending on what kind of interaction is happening between them, the particular, so for example X inhibiting Y inhibiting Z, this is how the dynamics of XYZ will look like. So X will increase after a certain time. Now since X is inhibiting Y, it will decrease. Now since Y is inhibited, Z will increase, because Y was inhibiting Z. If the concentration of Y is low, Z will increase. So you see here at this point, Z increases while Y is coming down. In sequential activation, where everything is activating it's like the next downstream element. In this case, X will increase, Y will increase a certain time later, because after X increases, that will increase the expression of Y. After that happens, after certain time again, Z will increase as well. So this is how the different dynamics can look like for different types of cascades, and you have different combinations of these cascades and different types of these cascades in your biological system, and you can model them using these kind of auto-regulatory networks and ODEs. Okay. So another and an important type of network motif that is found is basically feed forward. So the feed forward network motif will basically consist of basically a single regulator which regulates both downstream elements Y and Z, but like basically X will regulate Y and Z, but Y will also regulate Z. So there is kind of a basically a feed forwarding where basically there is a you can imagine this, if you are familiar with electronics, you can imagine this as different types of gates and or NAND, these kind of gates. So for example, let's take this example. So so basically X increasing Y or X is increased, any of this situation can increase Z. So there will be a condition associated with either X and Y both have to increase and both have to increase Z, or X can increase, Y can decrease. That can basically, that is an OR gate which is increasing Z. So these kind of different type of logics can be applied, because in systems, biological systems as well, you'll find these, there are certain genes or transcription factors which is not regulated by a single compound or a single protein. It will be regulated by multiple proteins or multiple compounds, and they will have a relationship ki either both of them will regulate together, but either one will regulate, another will repress, or there can be like either or, there can be both of them together. So these kind of loops, what you get, are known as feed forward loops. So this because of each of these three interactions in the feed forward loop can, depending on these interactions, can either activate or repress. There are 8 possible structural types of feed forward loops. You can like look it up. There are a lot. Like these are basically electronics concepts. So these are these 8 possible types of feed forward loops, how X and Y both can regulate, and basically X will regulate Y, which will regulate Z, and X will also independently regulate Z. And how these different dynamics will look like is given by these small plots here. If you see, if you model this using differential equations and Michael-Menden's kinetics, and if you simulate the results, you'll get something like this. So for example, X here is activating Y, and Y is inhibiting Z. Now how will Z increase? Z will only increase if X is increasing and Y is decreasing. That is how Z will increase. So at this point, what happens is X has increased, Y is increasing because of this. After a certain point of time where basically X and Y has both increased, then Z will increase and it will maintain a certain steady state, right? So these kind of models you can make, and you can simulate these models to check the behavior of how different types of cell elements, be it proteins, be it genes, be it transcription factors, how they are changing with time, how their concentration is changing with time. So where this is important, like when you are trying to see if a particular gene is getting, so if you're familiar with basics of molecular biology, so a particular gene will be regulated by multiple transcription factors, not a single one, but multiple transcription factors, and there will be certain regulations of those transcription factors as well, which will directly regulate the gene. So in those cases, X is your transcription factor and Y is your basically, you can do not take this example, this is not a good one for the one that I'm saying. Let's take this example. So X is a transcription factor, Y is a transcription factor, and assume Z is a protein. So in this case, X is also influencing directly for the production of Z, and X is also activating Y, which is the gene which is also producing Z. So how do the dynamics of X, Y and Z will look like for a certain period of time? Now after you have found it, if say for example this Z protein is producing, say for example this Y gene has been mutated and this Z protein is producing some faulty protein. Now you want to decrease the level of Z, but you cannot completely turn off X and Y because those are essential transcription factors in the cell. While giving a treatment to the patient, you want just for the Z to decrease, but not X and Y to not disturb the dynamics. So how you do that is depending on your dynamics situation, how your Z is increasing. Your Z is increasing at what point? Your Z is increasing here at the point where Y is increasing and X is increasing as well. So accordingly to that, you will provide a drug which will selectively decrease Z, but will not so much hamper Z that X and Y will also be hampered. So these type of nuances and these type of little things that you want to know from the system, these kind of loops, feed-forward loops and network motifs can tell you. The dynamics, modeling the dynamics can tell you about that. Okay, so guys, just give me 1 minute. I'll be back. My professor is calling me. Just give me a minute. 1 minute. I'll be back. Okay. Yeah, sorry for that. Sorry for the delay. Okay, let's move on. So next what we'll study about is basically Michaelis-Menten model. So this is a model that is widely used in chemical kinetics, how different reactions take place, enzymatic kinetics, how different enzymes can influence a reaction, how your enzyme and substrate forms. So basically this is, I'll just give you an overview. This is the whole equation for an enzyme catalyzed reaction. So basically S is your substrate, E is your enzyme, and what it forms is the enzyme substrate complex, which breaks down to give you the enzyme and the product, and the enzyme remains unchanged in the whole reaction. So this first equation dE dt is of no use, because ultimately you're till the if you consider from the end from the starting to the end of the reaction, dE dt will remain same. It's going to be 0. Basically E will not change with time, because the elementary property of the enzyme is that it does not get used up during the reaction. Now what will happen is, what is the law is telling us is basically enzyme plus substrate, this is a reversible reaction which gives you the enzyme substrate complex. There is a forward reaction rate associated with it, which basically forms the enzyme substrate complex from the enzyme and the substrate, and there is a there is basically the backward reaction which is associated with this Kr, which is the reverse reaction rate, which is enzyme substrate complex is getting broken down into enzyme and substrate. And also from this enzyme substrate complex there is a basically another reaction rate associated with it, which is basically forming your ultimately product and giving back your enzyme. So this is the whole model, and this is the whole reaction which is given on which the model is built on. So the Michaelis-Menten model takes the form of an equation describing the rate of enzymatic reactions by relating reaction rate and the concentration of an enzyme. The enzymatic reaction in this model involves reversible reaction where an enzyme E binds to a substrate S to form a complex ES, and a reversible release irreversible releasing a product pre and freeing the enzyme. And this is what is given by. Now if you apply law of mass action kind on this particular reaction, which states that the rate of the chemical reaction is directly proportional to the product of the masses of the concentration of the reacting substances, the system of 4 differential equations will emerge. So there are 4 unique compounds here. One is E, one is S, one is ES, and the other is P. So if you just to say, like, if you are modeling dE by dt, we know ultimately dE by dt will be 0 because E will not change across time. But if we are modeling dE by dt, it is basically negative of the forward rate forming of ES, because E is getting used up for the forward reaction. So minus Kf into E into S, plus now E is getting converted E is getting converted back from ES using the reversible reaction, which is the Kr. So this is basically Kr into ES. And this will be positive because E is degenerated again, it is increasing, so this is positive. And also E is also dependent on this ES getting used up to form E and P. So this ES is getting used up by the rate of Kcat. So this will be the whole reaction if you apply enzymatic law of mass action on this enzymatic reaction. This is for E. For S, it will be similar kind of a thing, but in this case it is getting used up by ES by the forward reaction, and it is only getting back by the reversible reaction, which is the positive one. Same with the ES complex, it is getting formed, getting reversed, and also getting used up to form the product. And for the product, it is only dependent on the Kcat and the enzyme substrate complex. So these are the set of 4 different differential equations that you can write from this single equation. And what you can do is basically dE dt will be 0. Now you can try to simplify these equations, and what you'll get is basically and what you want to try is basically dP dt, and if you substitute the values of Kcat from these whole equations, all the substitutions if you do, which is dP dt will be giving you the velocity of the reaction. This will how the reaction will look like. The equation will look like, which is E naught is the initial E naught Kcat is basically a constant into S, which is the substrate constant, and Km is which is defined famously as the Michaelis-Menten constant. That will be this is also a constant plus the substrate. So in their original analysis, Michaelis and Menten assumed that the substrate is an instantaneous chemical equilibrium with the complex enzyme substrate. An alternative analysis was proposed 10 years later by Briggs and Haldane, known as quasi-steady state of the system, that assumed the concentration of the intermediary complex, which is the ES complex, is approximately steady during the whole progression of the reaction. Both approximations assume irreversible dissociation of ES complex to the product and the free enzyme that yields the following equation of the velocity of the reaction. So if you simplify this is what you get, which is giving you the Michaelis-Menten kinetic equation, which gives you the rate of the formation of the product, which is in turn giving you the velocity of the reaction. So this is a very, very commonly used equation along with law of mass action to model different reaction rates for different products, formation of product rates across different parts of the system. So yeah, this I wanted to show you this. If you want, you can just do it yourself as well. If you just want to substitute the values of kf, kr and kcat, you can do those, and you can get from this expression this thing. It's just a substitution equation. So yeah, that's all for Michaelis-Menten. Now the model provides crucial nature about the nature of the enzyme in the form of kinetic parameters. The kinetic parameters is given by this Km, which is the Michaelis-Menten constant. So this is the concentration of the substrate at which the reaction rate is half the maximum rate. If you remember the Michaelis-Menten curve, it is goes out like a parabola, and then it reaches saturation at a certain concentration of the substrate. Half of that concentration of the substrate is associated with the rate of formation of product. That is what is known as the Km. The smaller the value of Km, the higher is the affinity. The rate will approach maximum velocity with lower S and reactions with a lower Km. The curve describing the relationship between the velocity and the substrate concentration in the Michaelis-Menten kinetics can be formulated as a non-linear regression model as well. So as a regression model, it can be formulated, and this is the exponential version of that model. So there are various versions of the model. Michaelis-Menten equation has been here for more than 100 years now, close to 100 years now. So there are various forms of this equation, be it in a polynomial series like this, be it in the form of dPdt like this, or be it in some sort of a regression model like this. So there can be various forms of this equation, this Michaelis-Menten model, and this is one of the very first mathematical models used in biology. So this is a very old, and this is a very robust model. This is used till date. Till date we study this model, and this is very useful in modeling different aspects of the system. How different, say for example, you are modeling the rate of reaction between a protein. So you are modeling a reaction where basically there is an enzyme, there is a substrate, there is a product, and you want to model that whole equation. You have the Michaelis-Menten model. So it's a ready-made model available to you to model different relationships between this enzyme, substrate and product formation. So this is a very important model, so please give it importance and study it well. Okay, so before we move into the Hill function, I'll just before we move to the Hill function, I'll have just one thing to go through. Just give me a second. Okay. Now, like there we assumed in the Michaelis-Menten model that there is only the enzyme, there is only the substrate, and there is only the product. These three are the only elements in the system which are reacting with each other to ultimately give you the product. But let's say for example there can be a second inhibitor. How is the second inhibitor working? Let me show you. Say for example, let's draw a schematic like here, right? Say for example, this is your enzyme, right? And this is something, I'll come to that, and this is your substrate, and this is what is known as the competitive inhibitor. So what it is doing is, this C inhibitor is present in this system along with the substrate, and it is very similar to the substrate, so it is going and blocking the reaction between enzyme and the substrate. The substrate cannot go and bind here because there is already another compound similar to the substrate that is already been bound there. So this binding cannot happen. So this is inhibiting. So there is a second inhibitor in the system which can bind to the enzyme and prevent the primary substrate from doing so. And like where this is used, if you ask, so this is an example of mechanics describing the action of drug on a receptor. So what the drug will do is, the drug will go and bind. It will be very similar in structure with the original binding product. So it will go and bind with the enzyme, but since it is not the substrate actually, so the product formation will not occur. So if you are giving a drug to inhibit formation of a product, this type of mechanism is very interesting and very widely used as well. So there will be a competitive inhibitor which will go and bind with the enzyme, which will not allow the substrate to bind with the enzyme, right? So if you assume the kinetic model, it will be substrate plus enzyme so there will be a forward rate associated, let's call it K1, and there will be a reverse rate associated, let's call it K minus 1, and enzyme substrate complex will form. I'm just naming it C1, which will break down with another reaction rate, but this is an irreversible reaction, so there is only going to one side, which will give you the product and the enzyme, right? This was the original enzyme kinetics reaction, but there is another reaction associated with it, which is this inhibitor, which will bind with the enzyme in a reversible fashion. So let's call this K3 and K of minus 3, and which will form another complex. Basically this is C1 is basically enzyme substrate complex, and C2 is basically enzyme inhibitor complex. So this whole, both the equation is describing this inhibition and basically the enzyme kinetics with inhibition. This is what we are doing. Now let's try to model it. One second. Now let's first write down the equations like this. So dSdt will be the first equation. Next will be dE dt. Next will be d of C1 dt. Next will be d of C2 dt. Next will be d of inhibitor and how it is changing with time. And the final will be dP dt, the change of product with time. Now from the equations, it's quite simple to write. So ds dt, how does S depend on? So S depend on this one, C1 basically, and S depends on C1 and SE basically, from where it is forming. So ds dt equal to K1 into C1, right, and minus of minus K1, K minus 1, S into E, right? So S is getting, sorry, I wrote a wrong symbol here. So this is where it is getting used up, K1 into C1. This is where it is getting used up, and this is where it is getting produced. So this is be a positive one, right? Okay. Now similarly with E, where is E getting used up? E is getting used up in the formation of C1. E is getting produced by the reversible reaction of C1 where it is getting dissociated. E is also getting produced from C1 through K2 and the product formation here as well. And E is also getting used up with the inhibitor as well. So there are three places where E is there. So we need to model it in a similar fashion. So E will be first is getting used up here. So let's do that. K1 into S into E. Similar situation here. E is getting used up here as well. So this
It is K1 or K minus 1?
sorry, for this one, right?
If that one.
Okay, yeah. So now let me write it properly. Okay, this one will be minus of K1. It is getting used up, so I've put a minus here, right? Just let me remove this. Yeah. Okay. Yeah, it is getting, E is getting used up here. So K1 will be associated with the minus sign. So minus of C1. Now it is getting produced here. So no, sorry, what I'm saying. Sorry guys, I got confused. So K1 is getting used up. Through K1 it is getting used up, and it depends on the concentration of S and E, right? So this will be minus K1 into S into E, right? Because E is getting used up by K1 and it depends on the both of the concentration of S and E. So it will be minus K1 into SE. Now at the third one also it is getting used up. So it is minus K3 into I into E, right? Is it clear? Like, are you confused? If you are confused, please tell me, I'll explain.
Actually, both S and go to the reaction.
Yeah.
So I think S and ER behave same, right?
So what is the law of what is the basically the Michaelis mental equation telling you is basically the concentration of, if you see these reactions, the concentration of S depends on how forward reactions, so for example this S or this E, how E is getting consumed is dependent on negative of the forward reaction and also dependent on the concentration of E and S as well. So it's the same thing, minus Kf into Es, and I have written the same thing here as well, right? Minus K1 into S into E, right? Okay. So it is, when a substrate is getting used up, it is dependent on the concentration of all the substrates in the reaction along with the rate of the reaction. That is, if it is used up, it will be minus. If it is getting produced, it will be plus. Okay. It's the same thing I have done here. Okay.
But for C1, you didn't mention
This one, right?
in the
So S
The
is
second
getting
one. No.
so in the case of this one, you can, instead of C1 you can use S and E. I just put C1 because later in the in this, when we are trying to do steady state and everything, there will, what we'll do is dC1 dt and dC2 dt will be put as 0 because those will be considered as steady state. So for the easier handling of the equations, that's why I've put C1. So you can just put S and here as well, it doesn't matter,
Oh, okay. That's why I
right?
confused.
I understand.
Okay.
Okay. Okay, now it is also dependent, d dt E, the concentration of E is also dependent on C1, but C1 is getting produced from E and also C1 is getting consumed as well. So it is getting so E is dependent on C1 with a minus K1, minus of K minus 1. Sorry, positive of K minus 1, because K minus 1 is producing E from C1, right? So K minus 1 plus C1 is getting used up here to form E again, so this is also a positive reaction. So K of 2 into C1 plus also here also E is getting used up and E is getting formed by minus K3. So you take either plus, either if you are showing using up of E, you put a minus of K3 into I into E, or you put a positive of K minus 3 into C2, right? It's a similar thing. Here what I have done, I am doing here again. Okay, so here it will be K of minus 3 into C2, right? You can put K minus of K3 into I into E as well, both mean the same, right? Do not get confused, both are meaning the same. I just put C2 here because we'll use C1 and C2 in the later stages, right? Now dC1 dt, C1 is here, it's straightforward, it is getting formed by S and E, right? And it is getting used up, sorry, so here its space is a little issue here, it's right small. Here, and it is getting used up by K of minus 1 and K of 2 C1, right? So K of minus 1 it is it is getting formed, and K of 2 it is getting used up. So yep, K of minus 1 is getting formed. So this should be a positive one and this is a negative one, sorry. Do not get worried, these kind of questions will not come in the exam. I just want to like give you an idea about how these equations are written and everything. So that's why I'm solving this in front of you, but there is no need to get like worried that you have to do all this. You don't have to, I'm just giving you an idea. Now C2 is here. C2 is only dependent on I and E, so it is getting formed by K3 I into E, and it is getting used up by K of minus 3 C2, right? It is getting formed by I and E using K3, and it is getting used up by minus K3 into C2, right? This is C2. Now the next is I. So I will be used up by minus K3. So I is getting used up by I is getting used up by K3, not minus K3. I is getting used up by K3. K3 of I into E, and it is getting generated by C2, right? Because this is going back to I, so it is getting generated by C2. Now the final dP dt it is dependent on C1. It is not dependent on SE or anything. It is dependent on C1. So dp dt is positive of K2 into C1. Right? So many equations, so many terms written. I'll just tell you how we solve this. So like you have how many equations? You have 1, 2, 3, 4, 5, 6 equations for 6 different elements in the system. Now what you do is you do some sort of approximation, because you cannot solve all these ODEs together. So I'll just take a new section here. Yeah. So what you will do is known as quasi-state approximation. Approximation where dc1 dt equal to dc2 dt equal to 0. Now why we are doing this is already I told here. So alternative analysis, what Briggs and Haldane told us, was the quasi-state of the system that assume that the concentration of the intermediate complex is approximately steady during the progression of the reaction. So C1 and C2 here are basically C1 and C2 here are basically your intermediary products, because these will not be at the end of the reaction. So these are intermediate products. So the rate of these should be rate of change of these should be equal to 0. So that is what is known as a quasi-state approximation. Right? This is what is known as a quasi-state approximation, where you put this thing dc dt equal to 0. Now the solving is a very big equation to solve. So I've done it myself, and I'll just give you the answer like this. So if you solve this, and if you put these values and solve all the differential equations, what you'll get is C1 equal to just let me write it here, theta I E S, this is I by the way, theta, and what these mean I'll write down later. This is theta M into I plus theta I into S plus theta M into theta I. So your theta I here is given by k of minus 3 by k3. This is theta I. Theta M is given by k of minus 1 plus k of minus 2 by, this is minus 2 by k1. Now if you substitute all these values in dp dt, what you get is this Vm, and Vm is basically Michaelis-Menten constant of S to theta m into 1 plus concentration of I by theta I, and here on the side there will be another plus S. So this is a formula for the rate of change of product when there is a inhibitor in the system. Okay, so I just wanted to show you how these kind of nuances are modeled. So if you till now know only enzymatic reaction, enzyme reacting with substrate giving you product, but what if some other nuances are introduced in the system? So this is how you handle those nuances. You have to do some sort of approximation. Here we did quasi-state approximation and we found the values. I did not go into details of how you found the values. This is basic algebra. You can try it out yourself using these theta I and theta m values. This will simplify it a little bit. So ultimately this is how you model different types of product formation using these certain nuances. If certain nuances are introduced in the system, this is how you model it. So you check out every element in the system, how it is changing with time, and then you try to do certain approximations to find rate of the formation of the product or rate of utilization of the substrate, whatever you are trying to model. You can also find DSDT from here, you can find DIDT from here. Any element you are trying to model, you can find it from here, right? So this was just to give you an idea about how these different things are modeled and how you can use these ODEs to model and do approximation and get the values, right? Okay, so this was the Michaelis-Menten model. The last part of today's session is basically the Hill function. I'll talk a little bit about the Hill function. We'll see it in further lectures where we properly model different types of proteins and their expressions and how they are like changing with time. We'll see more examples of Hill function later down the line. But what generally it is basically all the simple enzymes will follow the Michaelis-Menten equation as I showed you. They will exhibit a hyperbolic reaction curve, velocity curve. So it will be like a hyperbola, and the substrate will, the product will be like this. So just let me draw it here. So your product will be like this, and your substrate will be something like this. So this type of hyperbolic curve, this is basically your, this is basically your substrate concentration. This is basically your substrate concentration, and this is how it is. This is basically a product. Let me just write it here. This is your curve. So this is showing your substrate, and this is showing your product. So this is time and this is concentration, right? So product is increasing and it becomes stagnate at a, basically saturate at a concentration of the substrate, and the substrate goes down and saturates. So, and half of this concentration, half of this basically steady state value is given by this Kn, right? So this was the Michaelis-Menten equation. Now in the Michaelis-Menten equation you see these kind of curves, and many of these enzymes such as regulatory enzymes, allosteric enzymes in our body will exhibit Michaelis-Menten kinetics. But they have got more than one subunit. Basically they are referred as oligomers, having more than two or more subunits. So the oligomers enzyme will not follow Michaelis-Menten equation. So if there are multiple subunits of the enzyme reacting together, it will not follow the Michaelis-Menten equation. What will follow is basically the Hill equation. So in 1910, this person Archibald Hill formed the Hill equation to describe the sigmoidal O2 binding curve of the hemoglobin, which is used to describe the fraction of a macromolecule saturated by a ligand as a function of its ligand concentration. So it is basically a form of Michaelis-Menten equation for to describe a much more much more accurately describe the process of, say, binding of different molecules together. Say for example, a protein is getting translated, a gene is getting transcribed. These kind of reactions will have multi-unit enzymes or oligomers associated with them, which will not follow the Michaelis-Menten equation. So this Hill equation provides an alternative for these kind of macromolecules saturated by a ligand as a function of ligand concentration. So this is given as the whole Michaelis-Menten Hill equation, where theta, which is on the left hand side, is the fraction of the receptor protein concentration that is bound to the ligand. Your L is the free or the unbound ligand concentration. Kd is the dissociation constant in which the ligand and the receptor will dissociate with each other, and Kd is the apparent dissociation constant, and Ka is the whole dissociation constant. So they have just changed the values here a little bit. So basically this K value will depend on what you are trying to model, but ultimately this is the form of the Michaelis-Menten equation. So this n you see, L to the power n to the power n, this n describes, which is known as the Hill coefficient, which describes the cooperativity. So if n is greater than 1, it will positively cooperatively bind. If n is negatively n is less than 1, it is negatively cooperative binding, which is basically they'll inhibit each other. For n greater than 1, it will positively regulate each other, and for n equal to 1, there is no interaction, basically non-cooperative and completely independent binding. So you don't know it will bind or not, right? So we'll look into Hill function examples and models in the later live sessions, but in the next live session, and also after that I'll take another live session for 2 hours just before your exam. I think your exam is around middle of September, so before that we'll take another live session. We'll recap all the topics that has been followed for all the 4 weeks, and also we'll discuss some problems or any problems that you have. So any kind of like problems you are facing, I'll suggest you like write them up and like form a list, and after next week you mail them to me, so that in the recap session I can bring those up and help you solve the problems for this. Okay, so this was Hill function, and at the end what we come to is the Waddington's landscape. So this guy Conrad Waddington published his famous drawing of the epigenetic landscape that depicts how a cell progresses from an undifferentiated state to a number of distinct, discrete and differentiated cell fates during development. So basically this is your undifferentiated state, how you can move in, like there are multiple ways to move it. So this is the differentiated state, this is the differentiated state. So how from an undifferentiated state it can move to particular differentiated states, this is given by this Waddington landscape. So this cell is represented by the ball, and it starts out in a valley at the back of the landscape, which is here. As the ball rolls forward and downwards, the valley splits or bifurcates. So at this point it bifurcates. So here it is where the bifurcation plots are useful. So in this system, you know, from after this point there are 2 points of stability. When the cell has reached this point, it has 2 options. It can go either at this point of stability, or it can go to this point of stability, right? So as the valley splits and bifurcates into 2 valleys separated by a ridge, these new valleys represent alternative cell fates. So as I was saying, a T helper cell can be formed into a TH1 cell or a TH2 or a TH17 cell, depending on the stable values from depending on where the cell decides to go from this point, right? So these values, the new values represent alternative cell fates, external stimuli like inductive influences or internal influences like homeotic genes. Homeotic genes are those genes which drive a particular cell fate differentiation. So these kind of GATA3 and ROR gamma T, these kind of genes that I was telling you for the T cell differentiation, these are what are called as homeotic genes or master regulators. These homeotic genes determine which of the 2 valleys a particular cell chooses. The valleys continue to split, and eventually the cell ends up in one of many terminal subvalleys which represent terminally differentiated cells, which is these points. So this cell can come to can be at this point, or any other point at the end of this valley. The cell is permanently and in its terminally differentiated state by high value walls. The steeper the walls, the more canalized, in the Waddington's terminology, is the cell fate. So this is basically the ball rolling diagram or the analogy that is shown here. At the onset of the development, the ball can also represent a region of cytoplasm or a fertilized egg. And at the back of the landscape, the potential surface is monostable. So at this point, the surface is monostable. There is only one stable point. But as the cell gradually progresses in time, there are multiple fronts of stability that it can assume. So that is what is given by this Waddington's landscape. Okay, so this brings us to the end of the session. Before we go, I think I have covered everything that sir asked me to cover today. There's one problem that is left. I think we can solve that as well. Let's do that. Okay. Yep. So let's assume you are given two equations like this. Dx dt is equal to 1 by 2 plus y minus x. And another one is given like this, dy dt equal to 1 by 2 plus x minus y. Now let's assume x is a protein and y is a protein, which are both interacting with each other, and they are given by these two ODEs, right? Now can you tell me what is the relationship between x and y? Is x activating y? Is x inhibiting y? Or is there no relationship between x and y? Just looking at these equations, nothing else. Sorry, I'll put the equations up again. Yeah. It's quite simple if you see both the equations. For example, dx dt. Does dx dt increase y when y is increasing? No, because it is as a reciprocal. If y increases, dx dt decreases, and if y decreases, dx dt increases. Same is the situation for this dy dt and x. If x increases, dy dt decreases. If x decreases, dy dt increases. So these are what are acting as repressors of each other, right? So I'd suggest like yeah, so equations like these will be given in your exam, and you will be asked to state the relationship between the interacting proteins on the molecules. So if it is given as a 1 by like this, it means as y is increasing, your left hand side is decreasing. So it is actually repressing your x. So if y is increasing, dx dt is decreasing. If x is increasing, dy dt is decreasing. So they are repressing each other. So if you want to find the steady state of this system, so if dx dt equal to 0 implies from this x equal to 1 by 2 plus y. Same with dy dt equal to 0 implies y equal to 1 by 2 plus x. It's just, if you equate these to 0, y equal to 1 by 2 plus x. Now you substitute y in x, or you substitute x in y. I'll substitute x in y. So basically y equal to 1 by 2 plus 1 by 2 plus y, right? Just substitute the value of x here. Now if you simplify this, this becomes 2 plus y by 5 plus y, and y equal to, now you cross multiply, y square plus 5y equal to 2 plus y. Take it on the left hand side, y square plus 4y minus 2 equal to 0. Now if you use a quadratic formula, y equal to minus b plus minus root over b square minus 4a into c by 2a, right? So this is 8, 16 minus 8 is 8, and divided by 2 here. So this becomes minus 4 plus minus root 8 by 2. So this 4 will come out, 2 into root 2, this is 2 root 2, so minus 2 plus minus root 2, right? Now minus is not possible. I think I did some wrong. Oh, this will be minus 2. Sorry. This will be minus 2. So, yeah, just do it again here. Yeah, this is minus 2 actually, I did wrong here. So it is minus 4 plus minus root over 16 plus 8. Not 16 minus 8, 16 plus 8 by 2. Right, so minus 4 plus minus root 24 by 2. Now you take 4 out, so minus 2 plus minus root 6. Now minus is not possible because y cannot be negative, because y is a concentration of something. So y cannot be negative, so y is positive, so y is basically root 6 minus 2. Now if you substitute it here, x equal to 1 by 2 plus y. Right, so 1 by 2 plus y, substitute it here, 1 by 2 plus root 6 minus 2, 2 gets cancelled, x equal to root 6. So your steady state will be at x comma y equal to 1 by root 6 comma root 6 minus 2. Okay, this is how you find steady states. And just remember that these are repressors, and how you found it. If y is increasing, dx dt is decreasing. If x is increasing, dy dt is decreasing. Right? So yeah, that's all from my side. If you have any questions, you can ask, or else we'll close this session. So just to
Hello.
yeah, just give me 1 second. I'll recap what we have learned today. So we started with bifurcation. We learned different types of bifurcation, how bifurcation occurs, saddle node and everything. Then we looked at different examples and how we do bifurcation plots. So this is one of them. This is how the bifurcation plot for this equation looks like. We did another for this equation as well. So different values of, we are varying the parameter and we are checking how x, our dependent variable, is varying with the parameter. Next we looked at different types of network motifs, how different types of these motifs can bring about different types of dynamics, positive feedback loops, how are the dynamics looking like, same with negative feedback loops and auto-regulation, and why their dynamics are important, right? And feed-forward loops, which basically has multiple elements to it, which directly influences and also indirectly influences the final product as well. Then we looked at Michael-Mentenis model and its various implications. And at the end, we looked at Hill function and Waddington's landscape, right? Okay, now you can ask if you have any questions.
In the bifurcation diagram, we plot bifurcation diagram for only one parameter. Okay.
Yeah. So
suppose if our system has more than one parameter, we have to plot for each parameter.
Yep. So for what happens is, if there are more than one parameter, what you will do is you will plot for each parameter and you will try to find a common point across all parameters where there is this bifurcation happening, right? So if you say, for example, you have two parameters, you have say lambda and mu, and you have x, you want to see how x is changing with lambda and mu. So what you do a 3-dimensional plot. You can do like x versus mu and x versus lambda and check them separately, but you also can do a 3-dimensional plot, x, mu and lambda, and check how with the change of both mu and lambda your x is changing. It will be a 3-dimensional plot. So the more your parameters, the more number of bifurcation plots there will be with respect to those parameters. But in the end, what you are trying to model is basically where the bifurcation point is. So for example, I'll just share my screen again. For this example that we did, there is this, not this one. Yeah, for this example that we did, at this point at lambda equal to 4, this was the equation, if you remember, this was the equation. At lambda equal to 4, there is the bifurcation. It is like the curve is like at lambda equal to 4 there is one steady state. If you move away from lambda equal to 4, there will be two steady states like that. Now this is the point of bifurcation where it is changing where the plot is getting bifurcated. So what you want to figure out from this bifurcation plot is also like how it is bifurcating, but also where it is bifurcating. So if you have multiple parameters, you try to plot them together and to check where according to all those parameters is the bifurcation plot. So if you, I'll show you in Google bifurcation plots in 3D. So this is how 3D bifurcation plots will look like. So you will have two parameters on this side. This is your dependent variable, and you're checking how the whole landscape is changing according to these two variables, right? Is it okay?
Okay, but if we have more than two parameters?
More than two parameters, you cannot visually see. What you need to do is you need to have some mathematical techniques which will tell you at which point across all the parameters is your bifurcation possible. So there some sort of linear algebra comes in where you can use these as vectors and you can model them and try to find eigenvalues and eigenvectors. You can use linear algebra techniques, but those will be much more complicated. But the idea is to have the parameters, how your x or your dependent variable is changing with your parameter. That is the general idea. If you have multiple parameters, you do it multiple times and you try to find a common point actually where all the parameters are there, and after that point the whole behavior of the system is changing. So that is the bifurcation point. But that is the idea. But what happens if you have more parameters, it becomes much more tedious to find that point. As you are saying, if you have more than two, you cannot visually see that, so you need some other mathematical techniques to find that point, right?
Okay.
Yeah. Okay. Any other question? Okay, if there isn't, so I'll end the session here. Thank you for joining. We'll have the last week session in next Saturday. After that, we'll have another live session just before your exam. Can you just confirm when your exam is?
I think September 16th, 10.
16th September.
1 minute.
Yeah.
Sorry, 22 September, I think.
So 22 September, that means I'll take an exam around like 15, 16, not exam, live session, just a week before your exam to recap all the things that we have studied here. And also, if you have any doubts, I'll suggest you, any specific topics you want me to revisit in that session. So I'll suggest you write down those topics and you send a mail to me so that I can prepare the slides accordingly and teach accordingly. But yeah, I'll be taking that session sometime around like 10 to 15th of September, a week before your exam, so that you have a revision and you can go and give a good exam. Okay, so I hope you have my email. So any topics you find are challenging and you need more revision on that, you make a list of those topics and you send it to me so that I can cover those in the live session. I can come prepared. Okay.
Hello.
Yeah.
Actually, in the first 2 weeks, it was fully mathematics, and this week and next week, I think it is not that much maths, I think. So in the exam, what we can expect, like both a combination of them, or
Yeah. In the exam, you can expect a combination of them, but the thing is, for the mathematics side, the mathematics will not be that complicated or anything. This will be like simple problems, and your exam will be in an MCQ fashion, so that you do not have to write and anything. It will be in an MCQ fashion. You will be given small sums, small problems, and you will be given a set of options and you need to choose from them. And for the biological side also, like not very complicated biological stuff, simple stuff only, MCQ format only. You can expect an equal weightage, but it will not be like you have separate mathematics questions, separate biology questions. What you'll have is basically questions which have both concepts of mathematics and biology involved in them, right? So you will not have a segregated question paper like that, but it will be simple. No complex stuff will be asked in your exam. No complex derivations or complex workouts will be asked. You will be given simple problems and given options. You need to choose from them. Okay, this is what sir has told me. I am not part of the NPTEL team who sets the paper. What sir has told me, I am conveying to you. If you want more information on the exam, you can directly mail it to sir. You know sir's email ID, right?
I don't know.
Okay, just
Actually, why I am asking is,
yeah.
I think for this course, some biology people and mathematics people both are enrolled. I think
Yeah,
if equal weightage will be given, na, so both of them can qualify the exam.
I think equal weightage will be given, and it will be not that difficult. Like, say, I understand you are from a maths background, but the biology questions will be not that difficult that you cannot answer. If you go through the course, every question that will be asked is from the course itself. The types of problems that we have solved, the types of concepts that we have discussed will be everything from the course itself. There will be nothing outside or very difficult for you to answer. You will be able to answer if you follow the course, and like if you study well, you will be able to answer. Do not worry about that. You will not be asked extraordinary questions about biology or anything, right? Okay, don't worry about that. And if you have further questions regarding the exam, you can directly mail sir, because he has more information, because he sets the paper. He has more information about how the paper turns out than me. Okay.
Okay. Thank you.
Okay. Okay. Anything else?
No, I think.
Okay. Okay. If you have my email ID, if you like find anything difficult, just mail it to me. I'll combine all those things and I'll discuss in the final live session. Okay, then I'm concluding this session. Thank you for joining. See you next week. Okay, thank you.
Thank you.